Alright guys, hey, today we're going to start covering some stuff over measurement and a little bit of other material on deviation and your uncertainty and error. A lot of it's stuff that you're honestly already familiar with and it's kind of review. I'd love to say it was going to be super interesting and that I could make it, funny and entertaining, but honestly it's kind of dull stuff. But it's important stuff that I really need to mention to you guys. I just didn't want to waste class time basically having you copy down PowerPoints and do notes. I would rather have you guys kind of do this at home for right now, and then when we meet in class we can actually go through and do some practice problems and actually challenge you a bit and have you work together, and I can help you then and kind of help you start building up that confidence a little bit with the actual problems so you guys don't start panicking every time we have a test or a quiz. So that's kind of going to be our goal. Watch this, take notes as necessary as you would in class. Make sure you're familiar with it. When we meet back together, we'll go through some practice problems, and hopefully if you have any questions we can cover them then. Okay, so the fundamental thing to get down, see what I did there? Fundamental units, yeah. Anyway, the fundamental thing to get down here is that you're going to have a set of base units. You're going to have a set of prefixes that you can combine with those base units that will change their magnitude. The advantage of this system is the fact that it's going to change their magnitude by a ratio of 10. Which makes the conversions incredibly easy, right? That's the whole jumping to decimal thing, as opposed to our silly, annoying system here in the US where you have to know a whole bunch of annoying conversion factors and then you have to do actual math with the calculator, and it's just a pain, right? Instead, you can jump the decimal and it makes the math a lot easier. Now, your fundamental units are going to be mass, which of course is going to be the amount of matter in a given substance, right? It is not the same thing as weight. Remember, weight is technically, according to physics anyway, it's a combination of force and mass. Well, it's a force based on mass and gravity, I should say. Also, a good thing to note here is that technically gram is not what we would consider to be the base unit of mass. Technically kilogram is, as you probably noticed by the fact that kilogram is a default in many of our equations. However, the one that we start at when we're adding prefixes will be gram. I know that sounds a little bit confusing, but that's just kind of the way things work and how they cancel. We can talk about it a little bit more in a C in class, but it really comes down to how the system was derived way, way back, if you remember talking about that in Chem 1. Length I don't really have much to say about. Obviously, the base unit for length is going to be the meter. That's about all there is to it. Base unit for time is going to be the second, of course. It throws people off the first time when they see a prefix in front of a second, but yeah, you can have milliseconds or gigaseconds or technically any of those, even though they sound silly. They're possible, though rare. The same is going, whoop. Temperature will be the next one. Remember, temperature is going to be the average kinetic energy of the particles of a substance, right? As you add energy, the particles will move faster and faster. The faster they move, the greater the temperature. It is not the same thing as heat. Remember, heat is energy being transferred from one place to another. It's not a thing that you could basically identify. Heat is a concept more than a thing. Whenever you say, I'm going to turn the heat up in the house, it's really not the correct term to use. You can't just say, well, there's the heat, and point at one thing or the other, except the basketball team, but that's different. It's temperature that you're referring to a lot of the time when you say the heat. Okay? Now, your temperature there, of course, we do not use Fahrenheit because Fahrenheit is silly. We use degrees Celsius, or in the case of the gas laws, Kelvin. Your conversion factor there from degrees Celsius to Kelvin is 273. If you're ever stuck in panic mode and you can't remember if you subtract 273 or add 273, the general rule of thumb I always tell everybody is do whichever will leave Kelvin as the larger number. That means if you're adding or subtracting the Celsius, Kelvin will always end up being the bigger of the two. Okay, so hopefully that'll help you get out of a jam if you need to. If not, you can always just write out the equation if that helps you remember, and it's Kelvin is equal to Celsius plus 273. That would mean Celsius is equal to Kelvin minus 273. Also, a quick note there, remember, technically it's degrees Celsius because it's a relative scale, relative to our fiduciary points of freezing point of water and boiling point of water, 0 and 100 degrees Celsius. Whereas the Kelvin scale is an absolute scale, therefore it does not need any relative or degree. It's not a variation from a fiduciary point. It's an absolute scale that in theory encompasses the entire possible range of temperatures in the entire universe. And we'll talk about that more as we go along there. Finally, we've got amount. Now, amount is not another word for mass. All right, amount is the mole, right? The mole is technically a fundamental unit. You could put prefixes in front of it if you wanted to. Not that you ever really see gigamoles or centimoles or nanomoles, but technically you could. It's just really strange. All right, so here's the SI prefixes. On this slide here, I've listed out a lot of them. Don't panic, you don't need to know all of these. Okay? Come on there, PowerPoint, go, go, go. Okay, so here we are. Yep, that's not what I want. Okay, tera is a nice one to know, but honestly, you don't need to have it memorized. So we're going to start right here. Giga. Giga is going to be the largest unit you really need. It's 10 to the 9th. The smallest unit you're going to need is going to be pico. Okay? So notice a couple things for me. Here's where your base unit goes. So let's say we're doing meters. We would start with meters here. You would add a prefix in front of it to give you kilometers or megameters or gigameters. If we were going to a smaller unit, you could have nanometers or picometers or micrometers. So here's where we start with our base units. Notice, as you will, that your abbreviations for the larger units are going to be mostly capitalized. In a perfect world, they would all be capitalized. Unfortunately, we can't really capitalize kilo because it confuses everyone, because capital K is already taken by Kelvin, right? So it kind of breaks the mold. It's supposed to be capitalized, but that's too confusing in some of our units, so we use lowercase. Every unit smaller than the base unit should, in theory, be lowercase, and they are. Notice, of course, that you have many M's. So you have the meter, M. You have mega, capital M. So you could have megameters be capital M, lowercase m. You could have millimeters, lowercase m. Or you could have micrometers, where you need to use your Greek symbol here, whose name is escaping me at the moment. Basically, it looks like a U with a little tail there on the front, or a leg sticking out the front. That's going to be micro, since there's already so many M's that it's getting confusing enough as it is. If you ever get stuck and you can't remember them, try to relate them to things you're familiar with. Like deci is kind of like the dime. There are 10 dimes in a dollar. There's 10 decimeters in a meter. Centi is like the cent, 100 cents in a dollar. 100 years in a century. That's not a coincidence. That's the origin of the word. Okay? All right. Now, most of you already have these memorized. Some of you even grew up with them. If you, for some reason, do not have them memorized, you need to get that done, and it doesn't need to be a tedious task. I'm going to give you pretty much the worst advice that a teacher can ever give, but this works. Here's what you would do if you don't have them memorized. Make a dirty rhyme using their abbreviations. Write out the abbreviations in order and make a dirty rhyme. If you put somebody's name in it, honestly, you'll remember it for the rest of your life, because for some strange reason, that's how our brains work. So think of what it is, just make sure you don't write it on your paper or anything, because I honestly don't need to know that kind of detail about whatever. But it'll make it stick in your head, I promise. Give it a try. Couple of other things I should point out while we're here. Nano hopefully sounds familiar to you. If you've heard of nanotechnology, or the iPad Nano is supposed to be a reference to how small it is. Nanotechnology is literally a reference to its size. Nanotechnology, by definition, should be something smaller than or in the same size as 10 to the negative 9th meters. That's what it's supposed to mean. Okay, so those are the units you need to learn. Learn them. Convert, remember, by just jumping a decimal one way or the other. Another thing it might be helpful to note is the fact that you have what I call super units and regular units here. Deci, centi, and milli are jumps of only 1. All right, so you only move the decimal 1 place for each of those. 10 to the negative 1, 10 to the negative 2, 10 to the negative 3. Whereas every other unit here is going to be a jump of 3. That's why I call them super units. 3 jumps, okay? Technically, there are also 2 other small regular units on the other side of base unit here. That would be hecto and deca. Deca, not the same as deci. I don't make you memorize those, though, because honestly, no one ever uses them in science. They're kind of silly. So you can leave those off, make yourself a rhyme, get them memorized, move on with your life. Okay, now this next section you're definitely going to want to take notes on. Here's my advice. Get out whatever you use to take notes in class, your spiral notebook or just loose leaf paper in your chemistry notebook, and I would go ahead and just start a whole new section or page, maybe even put a tab on it if you can, and I would just title this section maybe Data Analysis, because this is going to be something you're going to want to be able to look at throughout the semester and year. Something you can flip back to as you do a lab, especially when we get down further into the labs where I need to basically use them as one of your evaluations. These are going to be things you're going to go back and probably need to look up. Now, they'll also be on your upcoming quiz. Your first quiz is over this material, but it's something you're going to want to remember down the road too. So put it somewhere where you can find it again. Accuracy, as you guys already know, because you've been doing it all year long, is going to be how close accurate the measurement is to the actual real-world value. Precision is basically how close a group of measurements is to each other, and that seems like a silly distinction, but it's important. If you don't remember that, think about when you use the scales in the classroom. Those 3 decimal scales are kind of a finicky beast, right? If you measure the same object 3 times on them, chances are it's going to weigh 3 different masses. And that's, because of air currents and the amount of precision you're dealing with there with that many decimals. It's just kind of the nature of the beast. That's what precision means, okay? How close the 3 measurements are to each other, or how close the group of measurements are to each other. Be careful though, because precision, like I just used it, can also be used to indicate how fine a particular device can measure. So when I say the precision of our scales is 3 decimals, that's a correct use of the term. It's just a slightly different use. That's because, if you think about it, the more decimals I get on that scale, the more likely the measurements are to be close to each other. Okay, it's kind of a fine line there, especially when you're talking about an instrument, whether you're talking about accuracy or precision. Also, just kind of on a side note, NB there stands for nota bene, as in note well, Latin. IB loves using that for some reason. Instead of using note, they always say NB for nota bene. Okay, next thing I'm going to talk about is uncertainty. And again, the last 2 labs I already had you guys apply uncertainty. So you already hopefully know it, you already hopefully have it in your notes, and you don't need to write anything else, unless you'd like to have them all in one place, which really isn't that bad of an idea. Alright, each measurement, each real-world measurement, anything other than an actual counted value, is going to have a certain degree of uncertainty to it. By tradition, we typically indicate it to be 1 decimal place further than the precision of the instrument, or I should say 1 decimal place further than the last estimated digit in the case of a ruler, and we say it's 1/2 of that value. Now you guys have already been doing that in class, so you should be okay with it. It'd be plus or minus 1/2 of whatever that furthest precision was. In the case of a digital scale, since we're not really sure how it's rounding, we always say it's plus or minus 1/2 of the actual last digit or decimal of uncertainty. Molar mass is a great example of this. You may have never noticed, but next time you look at a periodic table, if you look at the molar masses of some of the things in the periodic table, or atomic masses if you will, there's a different number of decimals in all of them, because some elements are unstable and we can't get them to stick around long enough to actually accurately measure their molar masses to a good degree of precision. Some of them are hard to separate out and really get 100% pure samples, especially those down there in the F block with the lanthanides. So they're going to have less decimals, a less precise molar mass. It's a really good example. Take a look at the periodic table next time and try to think to yourself why some of those values would be so hard to measure. It kind of tells you a lot about the nature of certain elements, lithium in particular. Alright, well, we're done for this one. I'm going to go ahead and start up on the next PowerPoint and start up on our next video, and we'll work on from there. I'll see you then.